Okay, yeah, so we are the surgery planning group, like the surgery planning part of the Z imaging project group. And sort of like a preface to this project isn't as much a machine learning, like, hardcore machine learning project as it is more of an investigation into kind of the methods that are important and kind of getting, some really rough data into this kind of place to be then used in machine learning. So there aren't any neural nets or anything like that in these solutions because it's not, like I said, a hard machine learning kind of thing. It's more of a preface to it. And so basically what we were trying to do is we're trying to receive an MRI image of the brain and then sort of segment that out into the skull, the ventricle, and some obstacles to avoid. And then we wanted to compute some sort of optimal needle path for surgeons to perform a external ventricular drain, the safest path without, endangering other parts of the brain for the patient. And this is sort of a flow chart of how the algorithm really works. The first thing we do, and we'll go into more in depth in each part of the algorithm in the rest of the presentation, but the first part is to pick a viable insertion point on the skull, which you can see here. And then we are going, there's a lot of Monte Carlo methods used here. So we're going to sample 1,000 points of the ventricle and evaluate the distance of those points to the point we selected on the skull. And then we're going to pick the shortest, the point on the ventricle that has the shortest path to the point on the skull. And then after we have this line drawn, we're going to sample 1,000 points on the obstacles. And we're going to evaluate the mean distance of the points on the obstacles to the line. So then using the path length and the mean obstacle distance, we score the path, essentially give it a safety score, which is, it rewards being further away from obstacles and punishes being longer, like actually physically longer. So once we have a score for each surgery path, we then repeat this step, the steps 1 through 4, preferably several hundred times to then, find the optimal score of all the random paths that we generate. And the first thing we had to do was figure out how to, get all this data into something we can do that with. And so we have these MRI objects, and we use 3D slicer to segment out the skull, ventricle, and blood vessels, or really any obstacles. And then we had to go from STL files to NumPy arrays because STL files in Python are kind of read as like a mesh. And so there's not really much you can do as far as finite points to work with. So we had to convert those to NumPy arrays of points. And then we had to orient the segments, kind of together on a coordinate axis system so that everything spatially makes sense.
The first step is to choose sample points. We need to consider the points that we choose from skull and ventricle. For the image on the left, we just randomly choose point from the ventricle. Here we can see that there are lots of points inside the ventricle, which are meaningless because the goal of our project is to find sorted path from skull to ventricle. Therefore, we only need to choose the points on the surface of the ventricle. For the skull, here we can see the organ in the front is complex. So we only need to choose the points on the top of our skull. It makes sense that in real world, the efficiency make a hole at the top back of skull. By doing this of choosing correct sample points, we can not only improve the efficiency of calculation that follows, but also reduce the time it takes to run our code. Yeah.
Okay, so our codes are mainly 2 parts. The first is we want to find the shortest path between a point on the skull and a point on the ventricle. And the second part is we evaluate the score or the safety for those paths we choose and then got the optimal solution for them. Can we move to the next page, please? Thank you. So, so for the first part, we want to define a function that how to find the shortest path from a from point on skull and point on ventricle. So first we pick random points on skull, but on a specific so we like on the upper back part on the skull, so that we don't have to won't come to solutions that the path will through the cheek or something. And then we fix a point on the skull and use the Monte Carlo method. Is we randomly pick 1,000 points on the ventricle and store like the distance in an array, and then compare the values and got the minimum, the smallest value. So that 2 points will give us the shortest path for that selected score point to the point on ventricle. So that's how the function that the shortest path was defined.
Yeah, so here comes to find the optimal surgery path. And the first goal for us is that in real world surgery, what the doctor wants is that, so the doctors, he or she will need to avoid as many obstacles as possible. And and also the other point is that the shorter the path is, the less possibility the doctor will face to touch the obstacles. So mainly the two purposes of our function is the first is to find the path with the longest distance from the obstacles to the path. And the second is that we want the path length to be as short as possible. Next slide, please. Yeah, and here is two things we do in the optimization part. Is that first we choose a fair range of obstacles near the path, and later I will further elaborate what this fair range means here. And second is that we calculate the distance from the obstacles around the path to the path. It is not a very difficult mathematical formula. It's just like, calculate the points to line in the space and use their mean as a parameter in the evaluation function, which I will explain further. Next slide, please. Yeah, and here comes to the specification. So as we can see that the obstacles we use are the brain areas except for the ventricle. And the blue range means that the most potential obstacles for the right path. Yeah, and you know that because in the surgery, we start from the skull point and we directly to the ventricle part, so that we will not touch other area in the brain, such like, the back tissue in the head, so that we just don't need to consider all of the points in the brain, and we use this field range as a filter to filter the most potential obstacles in the brain. And also talking about what types of obstacles we are using. More accurately, they should be blood vessels, but so far we cannot do that accurately in the 3D slicer. But I googled the picture and the brain is full of the blood vessels, but that picture doesn't look good, so I didn't put it here. But I think that since there are so many blood vessels in the brain, so that we just use the tissues, it still makes the general size. Next slide. Yeah, and here's the evaluation function. And so the purpose of this function is that we are going to select the path with the shortest length and longest distance from the obstacles. And here is a function that in this function, Y represents the surgery path, and the capital XO is the set of obstacle points, and D is the distance from the obstacles to the path, and the lowercase XOI is the points in the obstacle point set, and the lambda is a parameter that you can change, so that basically the higher the score is in this function, the better the path is. So the second point is that since the blood vessel doesn't take up a very large surface of the brain, we can use Monte Carlo to create hundreds of surgery paths and evaluate their proximity to the obstacles and choose the best one. Next slide. Yeah, so for the evaluation of the 10 random path, the most potential path was found to have a distance of 42.17 and the mean proximity of the obstacles to be 1595, and the score of the path was minus 1.85. I think that that is just a random case we chose from the function, because in most cases the score will be positive, but the case is that we just run 1,000 random path and we choose the best one from them. And also you can just to repeat this process many times and just do Monte Carlo many times and to figure out the best one from the possibility.
And so one of the things we have to look at when it comes to furthering this work is we have to improve performance speed. Because the whole point of doing this is being able to evaluate hundreds of surgery paths, but right now the code is a little bit too slow for that to be a viable method. So if we can kind of find a way to maybe speed up some of the loops or something like that, and kind of decrease the complexity of the algorithm, then the performance speed goes down, and then we can evaluate more points efficiently. And the other problem is that doing this pre-surgically doesn't really incorporate things that happen during the surgery. So that kind of goes into the whole, augmented reality augmented reality thing that Z Imaging is working on right now. And also we need a method to more accurately segment everything, which helps, computational speed. And that's kind of a lot what the project presented earlier today goes into. And finally, we can actually try to actually implement machine learning in this idea and hopefully get to the point where if we, are able to, use ML to segment everything out and, get to the point where we can just kind of take in an MRI image and then based off of, the training data we have of doing this, we can kind of immediately see what the optimal surgery path is. And that's all we have.
Thank you guys very much. So, questions?
Should I stop sharing my screen now, or how should I?
No, keep it up.
Okay.
Yeah. So, Clara has a question here.
Oh yeah, go back to the score you defined for the path at the beginning. So, I don't know if I can. So which one? This one or the one that's like a little bit further down?
I think the formula.
Okay.
Or oh, never mind. Sorry.
Oh, that one. Okay. Yeah, basically that's just kind of like a pseudo way of writing the formula that's on the evaluation slide over here. I mean, if anybody else on the team wants to jump in to answer this, they're welcome to. But my understanding of how we did it was we just sort of, know that what that score does is it rewards being further away from obstacles and punishes being, super long. So it kind of just works for what we were trying to accomplish.
Yeah, because the reason why I found this function is from the loss function in the machine learning, but the different point from the machine learning loss function is that we do not do anything like prediction here, so we just directly go into our purpose and not consider something like the mean square. Yeah, so that's where it comes from. Hope it helps you. Yeah, so the parameter we pick is generally based on our project's purpose. But if you are asking whether there are some kind of I don't think there is any significant theorem behind it, because it's just something very similar to a loss function in the machine learning, but we didn't do any prediction or regression here, so we just considered it as something related to our project's purpose. Yeah.
why did you call? I mean, was it your method a real Monte Carlo method? Like it looks more like you are calculating on. You are not taking empirical expectation. You're not averaging your results, right?
Yeah, I mean, I wouldn't. Monte Carlo, calling it a Monte Carlo method, sort of a bastardization of Monte Carlo, but it's just the idea was we just wanted to kind of repeat the calculation several times to kind of get a coverage of the objects, because the more points we sample from the object randomly, probabilistically, the closer we get to actually covering the whole thing. So we kind of stole the reference to Monte Carlo. It's not an exact, completely correct definition, but.
Okay, thank you.
Yeah.
I was curious. So when you have your results at the end there, do you have any idea like what is like the average score for a path? So you generate all these paths using random sampling. Like what's like the range of scores or the average scores? How should we understand that
Sure.
minus 0.185?
Yeah, so I actually do think that the scores are really going to be pretty consistently close to that, because admittedly I didn't get like a distribution of like the scores, but I did kind of just eyeballing the average distances and proximities. They were consistently in around like 14 to 18 for proximity and like 40-ish to 45-ish on the distance. And this kind of goes into something that we were discussing, how this method may not be super effective for obstacles that are symmetrically distributed around the brain, because the whole idea, like if you were trying to, essentially if we're sampling from random points around these entire all these obstacles and they're symmetrically distributed, then essentially what we're doing is kind of just looking at this like center. We'll just get the center of mass of the obstacle. And at which point, the distance, so like the distance of every single surgery path drawn to that obstacle will be like very similar. So the obstacles that we were using weren't entirely symmetrical, but they were kind of close, which sort of makes you're not going to see a huge range in the proximity differences for the obstacles.
Cool. Well, we should probably move on to the next group, but are there any other are there any questions either from Raheel or Jose? And we'll be setting up a meeting between everybody next week. I'll send out an email probably tomorrow to organize it. But do you guys have any questions before we move on?
No questions from my end. Great job. Great job is super interesting.
Thanks. Appreciate it.
Cool. All right. Well, thank you guys very much. And up next, we're going to hear about using CNN methods to predict, to do image classification and prediction for the Boston 311 violation data.
Okay, can people see the screen?
Yep.
Okay. Go for it, Taylor. Oh.
Our presentation on the image classification with Boston 311 violation prediction. Next slide. Okay. So Boston 311 is an app that allows residents to report issues in and around Boston. Our project looked at predicting the location and the type of issues specifically. We initially focused on the types of issues labeled enforcement in abandoned vehicles, which you can see an example on the photo to the left, and the Needle Project, which you can see an example of a photo of that on the right. The Needle Project basically reports needles around Boston so that they can be safely disposed of. And we also looked at predicting the neighborhood of Boston that the incident occurs in. This would be useful to predict the location and type so that when a user fills out the Boston 311 report, they could just submit a photo and autofill could be used so that the user could just confirm everything is correct instead of having to fill everything in specifically. So now Alison will talk about the data processing.
Yep. Hi, everybody. So we first really had to decide what
data set we'd like to use. So on Boston 311's website, there's data sets starting from 2011 all the way through currently 2020. Each data set had various reasons and various numbers of rows. Each had about 200,000. So we decided to stick with the 2019 data set. We then needed to make sure that every line item had a reason or location type, since those were the classifiers we were using, as well as a picture. And as we found out, a lot of people don't submit pictures with their inputs to the app. So that removed about 60% of our data set. We then decided to make 2 initial samples, one for reason type. So we had the 2 reason types that Taylor said, the abandoned vehicles and the needle project. We had 1,000 pictures each from those 2 reasons. And then we had 5 locations, 5 neighborhoods around Boston, and those had 1,000 pictures each. We had to figure out how to import these images from URLs in a standardized fashion. Our first issue is that we found that all the pictures were of various dimensions. I'm sure different phones and different cameras taking different size photos. So we wrote a function and created a loop to add these black bars, as you see on the picture on the right, around all of the pictures to make them the same size. So we were able to manipulate them and put them into a NumPy array. After that, we started our analysis. So Emily is going to go into a little bit of a regression analysis.
We structured the way we looked at this project similar to how we did in class. So kind of going over some regressions to begin with, and then like expecting that these would fail or perform pretty poorly, and justify why we wanted to use neural networks on image classifications. So we tested out various regressions using the reason type classification, like we were discussed on the prior slides. And the results pretty much confirmed what we were expecting. The regressions performed really poorly with image classification, oftentimes overfitting. So for the linear and ridge regression, we had really good accuracy on the training data, but our R-squared was terrible on our test data, which essentially was because it was overfitting the images. And you can see some of that on the right. This graph is kind of crazy because there are so many coefficients from the pixels of the images. But essentially what this is showing us is that the linear regression and ridge regression actually were very, very close results, and both were pretty much just overfitting on the training data. And then we also did a QDA and LDA, and for those we used a little bit downsampled data because the runtime failed. But again, the accuracy wasn't too great either on those. So overall, we kept excited that this would probably happen, and it just gave us more support as to why we were going to use neural networks go forward in our projects. So I'll hand it off to Taylor. She's going to talk about artificial neural networks.
So as Emily said, the regression results weren't that good. So we decided to look at neural networks, and we first looked at artificial neural networks, and we used Keras to create the neural networks using the 2 reason types that we had indicated. So initially we used, we cropped the images down to 244 by 244 thumbnails. And that's the model on the top right. And it yielded approximately a 50% accuracy. So since we had only 2 reason types to choose from, that was basically random. So we reduced the images to 28 by 28 in order to reduce any overfitting that would be occurring with the larger images. And that's the model on the bottom right. We compiled that with Adam, and that yielded about a 75% accuracy. So better than the slightly larger images, but still not as good as we would hope. So now after this, we decided to look at convolutional neural networks, and Alison's going to talk about what we did with that.
Yep, so we've created a CNN from scratch, and we used a similar model for both the 2 reason types and the 5 locations. We compiled with a categorical cross-entropy loss function and the RMS prop optimizer. The main difference between the models, other than the classifier that we're using, one being reason and one being location, was the size of the pictures. For the reason type, we used smaller images with less pixelization just to make the runtime better. We felt that the images, it was clear enough to see a car versus a needle. For the location type, we felt like we needed more dimensions and clearer pictures for the model to give us good results. So for the reason type model with the two classes, actually for both models, we took 80% to be our training of our data set and 20% to be our testing. We got an 80% accuracy, which is 60% better than choosing at random and better than both the artificial neural network and the regression. For the location data, where we had 5 classes, we resulted in only a 25% accuracy, which is still 25% better than choosing at random. Since a lot of areas in Boston look very similar and the pictures didn't really have a lot of classifying neighborhood factors, we were pretty satisfied with the result, but Emily's going to go a little bit more into the results on the next page.
Yep, so just like summarizing some of the results here from both the artificial neural network for comparison and then the from scratch CNN on type and location. So overall, as we saw, we usually have best accuracy with smaller images, so especially in the artificial neural networks, but when we had less parameters, there's less chance of overfitting and our model will turn out better. The exception here is with location. We needed all of the detail that we could really get there because like Alison said, there wasn't too much classifying information. For comparing the from scratch CNN and the artificial neural networks, the CNNs outperformed the artificial neural networks, which we expected since the CNNs are looking at the images rather than like unspooling the images into vectors like the artificial neural networks were doing in their process, and this is image classification. So overall, we were able to achieve accuracy greater than 80% on reason classification with the CNNs and slightly less than 75% on artificial neural networks. So you can see on the top right, the CNN from scratch results, the accuracy for reason type is quite high, loss dropped pretty low. And then for the location classification, again, as Alison said, we were able to get the accuracy up to about 25%, which obviously wasn't as good as reason, but we kind of expected due to what we were looking at there. So next, Edith's going to go into the work that we also continued using a pre-trained CNN.
Okay, so as Emily said, we had pretty good results for reason classification using the CNN built from scratch. But to see if we could improve on it, we turned to using a pre-trained network. So using the exception architecture pre-trained on the ImageNet data set, we were able to achieve over 90% accuracy in just one epoch for the classification problem of just the 2 reasons, the abandoned vehicles and needles. So it did really well without much work. So the pre-trained network using the ImageNet data set has a category for vehicles. So this wasn't a surprising result. So we decided to expand upon the complexity of the problem and add in 2 more issue categories of abandoned bicycles and graffiti. And this just shows the model setup still using the exception pre-trained on ImageNet and did another 1,000 images for both of those 2 additional categories. So in total, we had 4,000 images for training and validation using batch size of 128. And this did run pretty slow, so we just used 5 epochs, but moving on to the next slide, slide 9, actually got pretty good results, 85% validation accuracy on the 4 category classification problem. So the image in the lower right is the confusion matrix for 100 test images, so 100 images from the rest of the data set that wasn't used for training or validation. So you can see that overall the bicycles and vehicles were classified pretty well, where graffiti had the most misclassifications. So on the left hand of this side of the slide, I put in 4 images of graffiti that was actually classified as abandoned vehicles, and you could see that there were vehicles in the images, so it explains why these were misclassified. And I think if we had more time to run this model and included more of the data available, it may have been able to pick up on the difference between an image that is meant to capture graffiti and one that's meant to capture a vehicle. So now Taylor's going to talk through the conclusion way forward for this project.
Okay, so overall, we came up with a pretty good model for classifying the reason for the issue, although it was more likely to misclassify when we added more reasons. It didn't work as well for location. That probably because a lot of the images showed mainly just the issue, like it might show a needle on the ground and it doesn't really give the general location that it's occurring in. In the future, it would be good if to incorporate more reason types rather than just the 4 we ended up looking at. And especially for location, it would be good to look at elements other than images, such as if you could look at the location from the phone that the image is taken or something like that, and could somehow come up with the neighborhood of Boston. That would be pretty useful. Also, we only looked at the year 2019, so if more years could be incorporated, and that would make a better model. Additionally, we've been seeing a lot in the news lately with the COVID-19 issue that they've been recommending constantly to report any COVID-19 issues with Boston 311. So in the future, it would be interesting to look at the COVID-19 reports and see if there's a way to come up with share the spread or different issues happening involving COVID-19. So I think that's it for our presentation.
Thank you guys very much. Are there any questions? And I want to thank you guys for pointing out the COVID-19 reports. That was an interesting. I wasn't aware that was all being done through Boston 311. So if anyone's interested in doing something, oh, sorry, continue.
We actually searched COVID-19 on the Boston 311 website, and there were quite a few results that came up. So it would definitely be something interesting to look at in the future.
Yeah, and yeah, if anyone wants to do some hands-on epidemiology, this would be a great time to do it. So you put a question in the chat from Zach.
So for me, I definitely did a little bit of reading on which optimizers, I think were best, as well as looking in some of the labs on what we've used. And after that, it was kind of a guess and check. I definitely on the CNNs used a SGD as well, but got better results using the optimizer I landed on, the RMS prop.
Yeah. How long? I was curious. How long at the end of the day was it taking to train both the location CNN and then the exception network on the 4 labels?
So for the exception on the 4 labels, doing the 5 epochs, I think it took around an hour and a half.
Okay.
Yeah, I was gonna say something similar for the location. I also did 5 epochs, maybe closer to like an hour for the CNN from scratch, not using the exception model.
Okay, so that's actually not too bad then, given training time. So that's interesting. So in some sense, if you wanted to throw a bunch of computational power at this, it would be reasonable to try to crank the results up.
Yes, yeah, I think so.
Very cool. Oh, Yantong has a question in the chat.
Yeah, so we definitely did lose some information, but we weighed our options when using the smaller images. That's why we only did that for the reason type, and Edith didn't use those size pictures for the pre-trained model. When we did go through and run the location model, we kept the pictures bigger because we knew if we lost all of that information, the model would never be able to tell where in Boston those pictures were taken. But between a needle and a car, there was enough data there with the smaller images.
Thank you guys very much. And So next, we'll be hearing about model evaluation for stock predictions. And just to be sure, so Pranshu, I should have made you co-host here. So you should be able to share your screen.
Thank you. So I hope I am audible.
Yes, you are.
Thank you. So I think I have gone through some of the fairly interesting presentations, and I'll try to make this presentation equally interesting, although there are not many fascinating diagrams. So because, and probably this is more of a literature project. So I took up this project on model evaluation for stock price prediction. And it was a fairly interesting project. And the reason I took up this project because it had a little bit of text, it had a little bit of market information, little bit of numbers, and I had to learn how to, how to do it, how to play with the literature as well as the numbers and mix it together. And obviously, lastly, I was doing it alone, so I thought the literature project would be more feasible of doing it. So, and I typically was looking to answer two questions. One, I need to predict the output label, and the output label is if the stock price goes high from the opening stock. So anything, if I look at the stock at a financial market, and if the stock goes high at the end of the day, it's labeled as 1. And if it doesn't go, that means lower, it is 0. So what contributes this kind of prediction? Obviously, one is text, the news which has been flowing around, and the news came from Reddit news. And my initial hypothesis was only work on textual data. But then I realized that the stock is not just governed by the news of the day, it's also governed by the opening price before the market, and both, or maybe just one of them. So I wanted to evaluate how is textual information in the Reddit news, how much of it contributes to the stock of label prediction, and the market information on the opening price and the closing price, how much they predict. And I was just thinking that is it possible to have both of them together? That means the concomitant coexistence of textual information and market information. Would it be useful? So everyone did in this project, the first set was selecting the data set. So I had the 2 data sets. They are from the redditnews.com, where the data had been taken from 2008 to 2014 on a daily basis. They came from so every day on Reddit news, there are news information, and they are in actually different places of the site on the website. So they have categorized into 25 headings, probably because certain headings had certain viewership. Maybe something which is on top left had higher viewership, and something which is in bottom left had lower viewership. So that's why they have categorized into 25 labels. And if you look at it here, I'll just try to increase the size of the presentation. So you can see here there were these are they were text which is given here, and then there were the part 2 which I did later on, was to merge with the information of the S&P, and I took the information from Yahoo. So S&P had the share prices, and I wanted to see how this output label looks like. So this is the heart of the presentation and heart of the work which is done. I want to spend more time on the breadth of it, because a lot of models have been made, and models have been made on different data engineering. That means the data cleaning had been done differently, and it's very important. Data cleaning has also a role to play on the analysis. So first thing was on data cleansing and data transformation. The first thing I did was I converted this data, the text data, and created a sentimental score. And so I took a pattern of words which are in the GitHub, and I had given the source there. I don't know what is the source of it. Is it from Harvard University? But I think I took it from GitHub. And I tried to find out the number of positive words per heading for each news each day. So let's say it's day 1. So I go back here. If it's day 1, we have top 1. So there are 25 headings. So I want to give all the 25 headings some score based on the sentimental score. And how the sentiment arrive is the count of positive words minus the count of negative words. So let's say there's something, if there are two positive words, the count would be 2. If there's a negative word, it will be 2 minus 1. And that's how we created the sentimental score. So this comes up to a matrix of numbers with the number of observations as the number of days. The number of columns or features happens to be 25 features, which is 25 news items with the numbers. That's data set 1. The data set 2, I used one hot coding. Here obviously I didn't consider 25 news items. I consolidated all 25 news items as one news item, and I then used one hot encoding to convert this the words into numeric integers, which relates to based on embedded size, and came up with the embedding vector for each word. And then dataset 3 was created by merging the financial data and the sentimental data. So I came up with I merged both the data together. When I say sentimental score, I actually summed up the sentimental score for each day, rather than taking for each heading or each newspaper item on the website. I combined them together for each day. Then I had to do model evaluation. So first of all, I tried to do the model evaluation based on which is a likelihood classification and the probability. So I used logistic regression, linear discriminant analysis, and quadratic discriminant analysis. And out of the 1989 was the total data set size. I divided into 1790 of training data and 199 as the test data. I ran the models, and the model was 65% accurate. So before I go ahead into further, while 65% accuracy is ironically the highest among all the models, the base data had one thing, which is one drawback. That when we say count of positive words, what happens if 2 negative words are used, and 2 negative words happens to be a positive word? So that hasn't been taken in my particular analysis. And second is the position of the word. How positive the position of word is not taken in the sentimental score. So that's one thing which is in drawback of this model. The one hot encoding, what it was, obviously I converted the whole data set into one hot encoding, and I used the embedded size of 64 and I tried to do various models in terms of neurons, and try to work it out. There is error in model 4b. Its layer is equal to 1. It's not layer 100. So it was still layers 1. So I did some model evaluation and I found out if I use one hot encoding on the RN dataset, then I found 57% accuracy on the test data. Now, both likelihood and one hot encoding was based on dataset 1 and dataset 2 respectively, which was on text data. So next I thought, let's combine them together. So I combined them together. So this time I used sentimental score. I added them up, and once I added them together, I created a new dataset, which is a dataset of financial numbers as well as the sentimental score. So once I did that, I ran the different models and found the accuracy 50% to 60 to 57% on test data, and the output was predicting whether the stock goes high or low. The sequence length was 5. That means the way I was predicting was I was taking the length as a time series data. I was taking the first 4 as the inputs and then predicting the the opening or closing of a stock on the 5th day. I changed the sequence length, I think, from 1 to 5, 1 to 4, and a little bit of changes in the, I think, in the neurons as well. The next was, I then thought that since I'm predicting the opening and closing of the stock market, what if I actually predict the opening price of the market, and even the closing price. In this case, I did the opening price. So I found a mean square error of 5% on test data. The layers 1, neurons of 50, and the sequence was 5. So this is how I constructed different models, and every model has their own pros and cons. And particularly the key was how the engineering was done behind the data, as well as during the analysis. So based on this, obviously, I created the confusion matrix, and the one represent that label is the stock end price is higher than the stock price of the start date. And as you can see, the diagonals represent how correctly it has been predicted. So we could get our 55 to 60% accuracy. I think with the regression, it was a little higher. And then we also did against the text and financial data together. I think for model 5, we got 58% accuracy, and we ran the same thing for text and financial information. So each model we predicted for the 5th day or for the 4th day. The test size is varying for each thing, probably because I needed to create a matrix, and I had to reshape it, and therefore I think the test size is a little unequal in the all 4 of them. So this is the slide on the prediction of opening stock price for the 5th day, and these are the training evaluation errors, and this were the predicted outcome and the measured outcome. So within the time frame and the constraints, we did the analysis, but a lot of potential things can come up and in some way creates novelty. The one thing is that we could use 2-step LSTM operation. I didn't do that, but we could do that. So I create a one-hot encoding vector and then use the financial information and then do the output classification. Second, I didn't consider ARIMA models here. I think in the earlier presentation, I think the one on the stores forecasting, they had considered ARIMA models. I could try it here. I didn't consider it, but this model could be checked as well of how successful we are in predicting the stock price. Then leverage the RNN architecture for sentimental analysis for each news piece. So when I use the RNN, I actually combine all the news together. Or combine all the positions of the news together. So on one day, if on a website there are 25 different news located at 25 different places, I actually combine them together in my RNN architecture, not in LDA. And this, and that's why I think RNN, I realized that RNN has a slightly little less accuracy, because when we look at the news items at the website, certain news items have certain news items have a high visibility, and therefore, if it has a high visibility, people would look at it more, and therefore, how people perceive things will be a little different, and therefore that news will be heavily weighted. And I think we could use bagging and boosting technique as well to improve the accuracy of the model. So these were some of the potential future work that could be done for this piece. And it was fairly, intensive project. I think more on the data cleaning side, because a lot of words were there, and I had to run on the models and a different way to perceive things, from sentimental score to one-hot coding. And I think somebody also referred as word to vector. So how these transformations they merge with the RNN is something to be studied. So I think that's it from my side. And this is the last slide. I just wanted to put some interesting explanatory analysis on the financials, on the because my presentation was more of literature than any images or any engineering areas. So thank you.
Awesome. Thank you very much. So are there any quick questions? Yes, for Matt.
Yeah, so I found this project very interesting. And so I just want to sort of recap some of the earlier stuff just to make sure I've got it right. So I know that you start off by coming up with a sentiment within a given newspaper by basically doing the number of positive words minus the number of negative words. And I know that you had 25 different newspapers. So did that then result in a 25-dimensional vector where each entry of that vector was the sentiment of a different newspaper? Do I have that correct, or am I wrong?
Yeah, you have it correct. But rather than 25 newspapers, they're actually, it's more of a Reddit site, and they are different. So the site has 25 different news for the day. So yeah, so you are right. There are 25 features or 25 columns. Yes.
Okay, great. Thank you.
I just have one question. I don't know if you know this off the top of your head, but do you know what, at the end of the day, within your data, what was the proportion of ones to zeros in the test set?
Sorry?
Do you happen to know what the proportion of 1 to 0, of labels 1 to label 0 was in the test set? So when we evaluate your model results, previously, was it like 50-50 or was it 60-40, or do you have an approximate idea?
Yeah, so if I look at the true data, they were more ones. That means they were more ones than zeros. That's how it was. That means in most of the data set, in actual data set, the stock ending price was higher than the stock price of the start date. And the ratio was therefore must be 70-30.
70-30, okay. Cool. Well, thank you very much. And if there aren't any other questions, then we will finally hear about word embeddings for from 20 news groups.
Okay, should I get started?
Yeah, go to it.
Okay. Just 1 second here. So can you see my screen okay?
No.
No, you can't? Okay, let me try this again. How about now?
Yeah, this looks promising. Yep, there you go.
Okay, great. So I think the last presentation sort of dovetails into mine pretty well, because there was some discussion of a word embedding, which was the question that I asked about, and I'll be explaining what word embeddings are a little bit later on. But first I want to say that, sort of like the surgery planning group, my presentation is maybe not a machine learning presentation proper. I am going to do some regression and play around with a RNN, but more so what I was interested in was in this project was processing the data, and then in particular constructing these different word embeddings and then seeing how each one performed. So let's go ahead and first start by taking a look at the data set. So I used the 20 news groups data set, which is a pretty famous data set for natural language processing. It's about 19,000 emails. Let me get this pointer going. Yeah, about 19,000 emails, each corresponding to one of 20 semantic categories. So you can see a few examples here: medical science, Middle East politics, etc. Obtaining the data set was a pretty easy part of this project because scikit-learn has a lot of tools built in to deal with this data set. So just use a data fetching function here. So the overall goal is to build a classifier which can take an input email and output its semantic category. And I chose to work with only 4 semantic categories, mostly to cut down on the size of my data set. We'll see later on that the vectors I ended up dealing with are 9,000 dimensional. And so any sort of improvements I can get on performance are definitely welcome. So here's a sample email. So yeah, just take a look at a few things here. We can see, for example, that we've got this header has a lot of sort of non-natural language information, such as the email address, the number of lines in this email. So I could look
Sorry,
at
for some reason, the image hasn't updated on our end. We may be looking at a different screen than the full screen.
Hold on one second. So you're just looking at the...
We're looking at the Google page still, the Google Docs page.
Okay, let me try this again. How about that? Can you see it now?
Yes.
Okay. Okay. Okay, great. So for the sake of time, I'm just going to sort of keep on going here. 1 second, sorry. Okay. Okay, so here's another example of an email. As you can see, there's sort of these punctuation marks, which you would expect would sort of cause some problems for our classifier and sort of investigate punctuation later on. So real quick, just what is a word embedding? Given an array of words, if we're going to do some machine learning on it, we want to convert that array into a numeric vector. So a word embedding is just a way of taking a word array and assigning it a vector. So the two word arrays that I'm going to be working, or sorry, word embeddings I'm going to be working with are TF-IDFs and the word2vec method. Okay, so let's talk about how I processed the data. So first of all, I pointed this out earlier. Exploratory data analysis ends up showing us that lots of classifiers are going to fit to features which have very little to do with natural language. Such as, especially the classifiers seem to be sort of biased towards whether or not a user has a university email address. So I just went ahead and removed all of those so that we would only be working with the actual natural language data. And so the overall goal here is we start off with an array where each entry is a string, and that string corresponds to an entire email. We want to build an array where each entry is a word, or where the most elemental entry is a word. So first thing we want to do is convert everything to lowercase so that, you know, the word the with a capital T is not treated as being different from the with a lowercase t. We want to tokenize. Natural Language Toolkit is a really useful library for natural language processing, and it contains all sorts of very useful functions. We'll see a couple of them in this presentation. So this tokenization function basically takes a string and tokenizes it at the word level. Stop words. So this is pretty interesting, and I'll talk about this a little bit more later on. Stop words are the most common English language words. So they're words like be, was, of, etc. NLTK contains a set of 187 stop words that can be downloaded. I wanted to remove these from the emails because I thought that, first of all, well, they don't really contain very much information, and second of all, performance was always an issue in this project, and so anything I can do to trim down the size of the data set is going to be very welcome. Unfortunately, we're going to see that actually removing stop words doesn't improve accuracy of the classifier very much, and at the very end of this project, I'll sort of conjecture why that might be the case, but let's move on. At one point in this project, I thought that it might be interesting if I would take each word and tag it with its part of speech. So for example, I could take an array like call me Ishmael, use this POS tag function, and end up with some sort of an array of tuples that stores part of speech information. This actually resulted in the classifier having pretty awful accuracy the only time I tried this, so I abandoned this method. I think maybe the problem is just sort of making the data too feature rich, but it's something that in the future, I think maybe tagging and how it can affect the classifier might be interesting to explore. And then stemming here. I thought that it would be useful to basically take words and convert them to their morphological base. So running and run both have the same stem here, run. Computers, computed, and computing all have the same stem right here, which isn't even actually an English language word. The reason I thought this would be useful would be because these all contain pretty similar information. However, the TF-IDF embedding will treat them all as being different. So I thought that it would be useful to take concepts and reduce them, or to identify a similar concept. And then once again, you want to go through and remove all of the stock words after embedding. Okay, so here's the interesting part of this project, which is the TF-IDF. It stands for term frequency inverse document frequency. What a TF-IDF function does is it assigns a weight to a word based on two things. One, how often does that word occur within a document? And second of all, how unique is that word throughout the corpus? The key idea is this. Basically, if your document has many instances of a very uncommon word, then that particular uncommon word is probably really meaningful and can probably tell you a lot about what's going on inside your document. So let's think of an example here. So suppose you've got a collection of documents which are all about the sort of migratory patterns of a different bird. So if you've got words like migrate, you're given a document and you've got a word like migration or a word like was, it's probably not going to be very helpful for determining what the content of your document is, because they're going to be spread out throughout the corpus. However, a word like African swallow might be specifically helpful in determining what your document's all about. Okay, so here's the definitions of, these are the standard definitions of a TF-IDF. Scikit-learn actually contains a built-in function, TF-IDF vectorizer, which will convert a corpus to a collection of vectors obtained from a TF-IDF. The advantage of building it from the ground up is that we'll then be able to sort of modify the definitions, these standard definitions, and actually some of the modifications that I ended up kind of stumbling upon ended up doing a little bit better than Scikit-learn's built-in vectorizer function, just 1% better, but I was pretty pleased about it. So I'm going to go ahead and skip over this example in the interest of time. It's just sort of giving an example of how to construct a TF-IDF. So this is what I just said earlier. Scikit-learn has a built-in function. I construct a TF-IDF, which is a little bit more accurate, but Scikit-learn's function is substantially faster. So in any sort of real applications of a TF-IDF, I would still recommend using Scikit-learn's TF-IDF over mine, just because mine is so slow. So here's a quick summary of results. So just using the standard TF-IDF that I defined earlier and applying logistic regression, I got 61% accuracy compared to 81% for TF-IDF vectorizer. Now keep in mind that if the classifier were to just guess, because there are 4 semantic categories, just guessing gets you 25% accuracy, which appears to be what's going on down here with quadratic discriminant analysis. That sort of will end up being a theme throughout this presentation, is that QDA is, for some reason, a very bad classifier for this data set. Okay, so now let's go ahead and modify the TF-IDF a little bit. So the first thing to do is to scale logarithmically the IDF, which recall the IDF is the thing that sort of gives you a sense of how unique is your word. So maybe in the standard IDF, it's just giving too much weight to very rare words. And so maybe we need to correct that by scaling logarithmically. Just doing this improves accuracy by about 19%. And so I chose to go ahead and stick with this for the remainder of my project. Also scaling the TF logarithmically. So the TF is the term frequency. It's possible that just the pure term frequency gives too much weight to words which appear in very long documents. So for example, look at document 1 here and document 2, pretty much identical semantic content. However, the word call is going to receive a much higher weight in the standard TF than it would in document 2. So the solution to this, once again, is to scale logarithmically. And once again, this improves accuracy. And then the best TF actually ended up being a Boolean TF, which loses all information. Which loses all information about how frequent a term occurs. It basically just gives a 1 if the term is in the document and a 0 otherwise. And this ended up being the best TF-IDF. It was about 1% better than scikit-learn. So I'm going to go ahead and skip through some of this other stuff, but here's a summary of the different TF-IDFs I constructed and how they performed. Word2Vec method is a very interesting word embedding, but in the interest of time, I'm going to go ahead and skip through this actually. I'm going to cover some of the results. So Word2Vec is just different embeddings. So I used an RNN, and here's some of the results I got. These are the hyperparameters. We'll see that we never quite got back to the glory of the TF-IDF, but right here, 53% accuracy isn't that bad. I'm going to draw attention to this pre-processing column. What it means is clean means that the data was processed exactly as I described earlier. None means very little processing was done. And so basically what I want to draw your attention to here is that no processing, the best that we got was 52.5%. All of the processing, the best we got was 53.75. So that's only a 1.25% improvement, which sort of suggests that actually all of that linguistic processing, like stemming and removing stop words, didn't really do anything for us. So I'm going to go ahead and skip through all of this in the interest of time. But I do want to draw attention to, once again, none processing here, 60% accuracy, cleaned 61% or 61.3. So once again, only 1.3% improvement. So yeah, some conclusions here. Probably the most interesting thing was the indifference to linguistic processing. I can sort of rationalize that in the case of maybe why stop words wouldn't be important to the TF-IDF. Stop words already has sort of a built-in mechanism to make sure that very common words don't become disproportionately weighted. So removing those words or not removing those words, probably the only thing we're going to get is improvement in runtime. When I removed punctuation, my results sort of decreased significantly, which I'm not quite sure why. Interesting. And then the last thing I want to point out here is that the optimal TF-IDF was completely blind to term frequency. Once again, it just gave a score of 1 if a term was within a document and 0 if it wasn't within the document. And actually, when I tried to adjust that, the score plummeted. However, I do still think that the optimal TF-IDF out there will contain some sort of information about the frequency of it. But yeah, that's pretty much the end of my presentation.
Awesome. Thank you very much. I'm sorry to hurt you along there.
Don't worry about it.
Yeah. So, are there any questions?
I have a question about the Boolean encoding. Maybe I didn't understand that how it works, but my intuition is that if you use that, like you would have some kind of explosion of the dimension, right? And then I would expect to work not so well. Yeah. Do you have any comment on this or?
So I don't think we have an explosion in the dimension just because 0
okay.
right here. Yeah. However, it's interesting that you mentioned that because one of the ways of sort of trying to modify the Boolean IDF, but the Boolean TF is supposed to solve this problem of very long documents are being given disproportionate importance. However, the problem with the Boolean TF is that it loses all information of frequency. So one of the ways that I tried to solve that problem but still keep track of frequency actually does result in an explosion of the dimensionality.
Right.
Yeah.
And do you think like the word2vec didn't work because you know you need more data, or it's more because it's hard to make it work like intuitively?
I'm not entirely sure. So one thing with word2vec that I would want to play around with is that I at one point removed all emails which had more than 1,000 words in an attempt to sort of reduce the dimensionality. And one thing I'm very perplexed about is, and then I ran that in through word2vec, and actually the results decreased significantly. I'm not totally sure why word2vec, because word2vec does contain so much more information about a string than TF-IDF is. So I just have to say I'm not sure why it didn't perform as well.
Actually, I also have a bit of a theory as to why the Boolean TF might work better in this case. And in this case, because you're categorizing by news group, right? So in some sense, like if you mention like a V6 engine, you're probably in the cars news group. It doesn't matter how many times you mention it, you're probably not in the bird watching news group.
Yeah, that's a very good point, actually.
I wonder if that's...
Yeah, because these semantic categories tend to be pretty, especially the ones that I chose, are pretty distinct from each other. So yeah, I think that's probably what's going on here, actually.
Yeah, and I wonder if that may as well be why you get some, I mean, I don't have an explanation for your word2vec thing performing poorly when you throw out large emails. That seems really weird to me. But I wonder if maybe that's part of what it is that in some sense, you're doing this classification problem with really distinct labels rather than something a little more closely like, I don't know, more fluidly within the natural language processing world. I don't know.
Yeah, that would be an interesting thing to take a look at. Like if I were to, instead of having my 4 categories be very different, if they were, say, computer graphics, computer hardware, computer recommendations, and something else, see how that affects it.
Yeah, or something like, sentiment analysis, right? Where, it's almost not, the structure plays a lot more of a role, right? It's not even so much the words that are involved. It's like how do they fit together?
Yeah.
Yeah, thank you very much. So this is a great little tutorial for everybody who didn't, for everyone who didn't work on NLP at all. This is a great little tutorial on what you can do what kinds of embeddings you can use that we didn't cover in class. Are there any other questions? All right, well, I want to thank everyone for a great semester. And I want to say as well that the projects that you guys did this semester were by and large very strong. I mean, especially, I don't know if you agree, Yorio, but the first semester that we did this, we were trialing things a little bit, but I think compared to the first semester we ran the class, the projects here are in general very high quality and very thorough. So
yeah, I agree. Yeah, it was very interesting, and also the presentation were very good. So good job to everyone.
Yeah, and I would also want to thank you all. I didn't want to thank you all individually afterwards, but by and large, everybody addressed my comments in their presentations. So yeah, thank you for that. And yeah, I hope you all have a great summer, and it's been fun. And if you have any updates so I will be forming the gallery here. If you guys have any updates that you want to forward on to me, do so, and I will let you know when that goes live. Yeah. Absolutely, and thank you to everyone who's been coming in from all over the world. So all over the world and all over the United States. Get one last. So for everyone in the evening class, we are finally it's still light outside when class ends. So the first time this semester. All right. Well, take care, everyone. Have a great summer, and I will hopefully talk to you on the other side of the summer. But if you have any questions or concerns or anything like that, please let me know.